his stuff on the various substitution and shift ciphers and the hill ciphers and so on. He's been talking modulo 26 a lot. Okay, there's 26 letters in the alphabet. You label them 0 through 25, and then through the use of modular arithmetic, then you know, you can talk about various cryptographic schemes of them. So what we're going to do is we're going to just formally introduce this concept now of congruence, and just go through the definition very carefully and prove a lot of the properties that it has, and show how these properties come from the definition and the properties of, well, divisibility that we've been looking at up to now. Okay. So now, to get a bit more of a theoretical motivation for it, I'll look back to one of these exercises at the end of chapter 3, which was that one, exercise 6. So exercise 6, if you look back on page, whatever it is, 2022. So exercise 6 was showing that if p greater than 5 is prime, then p squared plus 2 is not prime. Okay, that was this exercise. Now, on the face of it, that looks like quite a challenging problem, because we know there's an infinite number of prime numbers. How can we ever prove that p squared plus 2 is not prime? We can certainly check it out and verify it on lots of prime numbers. We could perform a computer search that just went through all the prime numbers we know, tested every p squared plus 2, and if given enough time, the computer would spit out a factorization of p squared plus 2 each time, and we'd never encounter a case where this number p squared plus 2 was prime, where p was a prime greater than 5. Okay, but that still wouldn't amount to a proof of it for every prime number, because there's an infinite number. Okay, so remember, there's an infinite number of primes. So how to prove something like this? How can you ever attempt to prove something like this? Well, we effectively proved it. Now, the question here tells you to think of the process of dividing the prime by 6. And when we did that, the remainders you get are 0, 1, 2, 3, 4, 5. So the 6 possible remainders. So you've got the whole set of integers. Inside the integers, you've got the whole set of, well, these are all the infinite number of integers. And when you consider an integer and dividing it by 6 and considering it by its remainder, what you're doing is you're splitting up the 1, 2, 3, 4, 5. You're splitting up the infinite set of integers into a finite set of what we'll come to call in this next chapter now congruence classes. 0, 1, 2, 3, 4, 5. Okay? The 6 possible remainders that you get when you divide any integer by 6. So it gives you a way of splitting the kind of infinite set up into a finite collection of sets. And depending on the problem you're looking at, it may be that all these numbers behave in a certain way, share a certain behavior. And all these numbers, all the ones with remainder equals 0, share a certain behavior. And indeed, the way we, got a red pen here, it'll stick out. So the way our proof for this problem proceeded is that we noticed that, well, you can never have a prime greater than 5, which gives you a remainder of 0, 0, 2, 3, or 4. So in fact, all the prime numbers are inside here, r equals 1 and r equals 5. Okay? The primes are the red dots. They only live inside r equals 1 and inside r equals 5. And by using this representation of them, you either get 6 cubed plus 1, or 6 cubed plus 5, p, they're the only possibilities. By examining p squared plus 2 for each of these, we found in every case, I think we found we could divide it by 3. So that shows that it was a composite number. Okay? Okay, good. So this shows that it's certainly a useful approach to take. Splitting up all the integers modulo 6, that's the phraseology we're going to use. Okay? So ignoring the actual integer, just looking at the remainder you get after you divide the integer by 6. Okay? And it takes the infinite number of cases, so the infinite number of primes you'd have to check to verify this result. It splits them up into 2 camps, the r equals 1 camp and the r equals 5 camp. And the r equals 1s all behave like this, so you can work out p squared plus 2, and just from the algebra you see it's divisible by 3. And the r equals 5 case, you work out p squared plus 2 there, and again you see that they're all divisible by 3. Okay? So we've certainly seen this approach bear fruit in that exercise. So it seems like a sensible thing to do. And I like to think about it is that it reduces the infinite number of integers, reduces them down to some finite collection of congruence classes. That's the terminology we're going to use. Okay. So let's get into it. Here's the formal definition to begin with. Now, there's 2 ways of setting it up. Some people go with the formal definition that talks about that 2 integers are congruent if they leave the same remainder after division by something. Okay, but we're going to just present it ever so slightly differently. So we're going to have a number n, and n is going to be the modulus, it's called. So n, in this example, the n was 6. Okay, so we divided everything by 6 and looked at the remainders. So here we've got n is the modulus, and it's a relation that we're introducing. Okay, so it's a relationship amongst integers. So here's a pair of integers a and b. We're going to say that a is congruent to b, modulo n, or a is related to b, but in this context, the relation has this name, the congruence. So a is congruent to b, modulo n, and this is the definition of it, if and only if n divides the difference a minus b. Okay. So the difference between the 2 numbers has to be a multiple of n, an integer multiple of n. And there's special notation, not saying that a equals b modulo n, but a is triple equals. Okay. So this is read in English as a is congruent to b modulo n. Okay. That's the kind of standard notation. Don't be tempted to use an equal sign, let's say. Equals is a pretty special relation of one thing equal to another. I don't think you should use it too much by saying that things are equal modulo n. But in a sense, that's how we think about it. A and b, really, they're the same modulo n. These 2 prime numbers, they're the same modulo 5. Sorry, modulo 6. They're the same modulo 6, because the difference between them is a multiple of 6. Okay, because if you have 2 prime numbers, if you have a p1, which was 6 times a q1 plus a remainder of 1, you had another prime number p2, which was 6 times a q2, again plus a remainder of 1. When you look at the difference between them, p1 minus p2, the difference between them is what? This minus this. So the 1's cancel, and you just have 6 times q1 minus q2. So indeed, you see that 6 does divide p1 minus p2. 6 divides p1 minus p2. So here, any 2 primes that are in this r equals 1 class, those 2 primes would look something like this, 2 different quotients, q1 and q2. But if they've got the same remainder, then when you look at their difference, the difference is indeed a multiple of 6. Okay? So that's the notation, and if we want to say that 2 things are different, modulo n, or not congruent, the same way we just have the triple line congruent sign, and we just stick a line through it to say that they're not congruent. So straight away, we prove something straight away, which is more or less what I've been explaining here. is that this relationship between congruence and integer division with remainder. So here's the statement of the theorem. For any given modulus n, A is congruent to B modulo n if and only if A and B leave the same remainder when divided by n. So here was two integers, two prime numbers, say, but in general, this could apply to any two integers. Any two integers that leave the remainder 1 when you divide them by 6. The two integers will appear like this. When you form their difference, the remainders cancel out, you see, and you're just left with a multiple of 6. That's essentially the proof here. The proof is just presented in total generality. So here was the example for the modulus of 6. So here's how we prove it. So here's two integers, A and B. This would be just general notation for integer dividing A and B by n. So A is a quotient Q1 and a remainder R1. B is a quotient Q2 and a remainder R2, and we divide it by n. And the crucial thing about the remainders is that the remainders are strictly less than n, of course. Now, we're proving an if and only if, so we have to go both ways. So first of all, we'll suppose that A is congruent to B. So by definition, that means n divides the difference A minus B. So that means n must divide this. Now, this expression here is just obtained from A minus B here. Okay? And we just factorize it a bit. So we got Q1 minus Q2 times n plus R1 minus R2. But by one of these basic facts about divisibility, it must be that n divides this difference of remainders, okay? Because n divides this term. This term is clearly a multiple of n, Q1 minus Q2 times n. So if n divides that part, and we know n divides the whole sum, then n must divide this second term here. Okay? Because you can write this second term as a linear combination of things that are divisible by n. So you get this conclusion that n must divide the difference of remainders. That doesn't say the remainders are the same yet. But you see, we also see about these remainders are strictly less than n. So you've got two things between 0 but strictly less than n. So what's the biggest difference these two things could have? What's the largest difference that these two things could have? N minus 1. Yeah, that's the largest difference. So, and what's the smallest difference they could have? 0, if R1 is actually equal to R2. So the smallest difference they can have is 0. The largest difference they can have is n minus 1, because they're both trapped in this interval. So how could it be that n does divide the difference? Which numbers between 0 and n minus 1 are divisible by n? There's only one of them, only 0. Okay? None of the other options for the difference R1 minus R2 is divisible by n. So that tells you the difference R1 minus R2 has to be 0. Okay? What else do I say here? This difference has to have absolute value less than or equal to n minus 1. So it's trapped strictly between minus n and n. And the only multiple of n inside here, okay, so we've already decided that n must divide the difference, R1 minus R2. But if R1 minus R2 is in this interval, the only multiple of n that is in here is 0. And 0 is a multiple of everything. Everything divides 0. So it must be that the difference between the two remainders is 0, i.e. they're the same to R1. So if two integers are congruent, modulo n, they have the same remainder after division by n. Now, the theorem was an if and only if, so now we should go and prove it the other way. So now this is just the general form of the argument I gave here. So if two remainders, if A and B divide by n and they have the same remainder, so if R1 is equal to R2, well then when you form the difference A minus B, the R1 and R2 cancel out. Okay? So you're just left with Q1 minus Q2 times n. Just exactly what I did here in the example of dividing these two integers by 6. So the ends cancel out, the remainders cancel out, and you're clearly looking at a multiple of n. Okay? difference of q's multiplied by n. So n does divide a minus b as required. So we've met the formal definition there, and we've seen that it's equivalent to having the same remainder after you divide by n. So a is congruent to b, it's related to b if n divides the difference, or equivalently if they have the same remainder after division by n. In some ways, this way of thinking about it, having the same remainder after division by n, that's maybe the more meaningful one, or maybe the easier one to think about, or the one that gives you more of the meaning of it, perhaps. So next we have some material on equivalence relations. Now I've said that the congruence is a relation. Remember, a relation is like a formula for a statement. Statement is something which is true or false. Yeah. So A congruent to B mod n, it's a relation on A and B. So when you put in values for A and B, it gives you a particular statement. The statement may be true or false, depending on whether or not they do have the same remainder after you divide by n. Okay? So this is a relation. Now, the nicest kind of relations you can have are these so-called equivalence relations. They're the ones that act in a very similar way to equality. So equality is the most important relation out there, maybe. So whether two objects are the same or not. Congruence isn't the same as equality, because you've got lots of different integers that are congruent to one another. Okay, but it behaves. It has this property that it's. We'll see the formal definition shortly, but it's an equivalence relation. And whenever you have an equivalence relation, there's a lot you can do, or there's a lot you can say about equivalence relations because of the properties they have. There's two ways of thinking about the definition of an equivalence relation. You either think about it in terms of these three properties: reflexivity, symmetry, and transitivity, or there's an equivalent way of thinking of it in terms of partitions. So this is an example of a partition I've drawn here. So I have some large set, the integers, and I have some way of splitting the set up into subsets. And these subsets have the special property that they don't overlap. So each subset is entirely separate from all the other ones. It's disjoint from the other ones. And every element of the original set is in one of the subsets. So the subsets cover the whole of the original set, and they also don't overlap. So it's like you've erected fences through the set, and everything is one side of the fence. So there's no overlapping between these areas. So this is an example of a partition, or just a simple sketch of a partition is some big set split up into subsets. And they don't overlap, and every part of the original set is in one of the subsets. Okay, that's a partition. Use that word in like in politics when they split a country up and make two new countries out of it, or erect a new border. They say they've partitioned the country. Ireland was partitioned by the British into Northern Ireland, Southern Ireland. India was partitioned at some stage into India and Pakistan. So sorry. In Bangladesh, yeah. Well, showing up my knowledge of history, yeah. But happens, and Sudan was partitioned into North Sudan states. So that's the similar idea. You had some original country, and suddenly somebody decides to split it up into sub-countries. And when you split countries up, you certainly don't want to have the countries overlapping. Countries overlap, then there's problems because each side says they own this part, and then there's a war for something. So you set borders between countries, you don't want them overlapping, and also you don't want to leave areas that aren't in any country. If one partitions a country, you don't want to leave an area of land that is somehow not part of any country. Because if there's people there, they're then stateless and they don't have the protection of any government. And also it's probably going to cause conflict in the future because there's a piece of land which nobody owns, so maybe more than one country is going to try and claim it. So partition, the notion of partition is very important in reality as well as in mathematics. But so you can look at it this way. You can have a large set split up into subsets in this way. Or you can talk about the relationship between the elements. So this definition 4.2 talks about properties of the relationship between elements. Okay? So here we're using this general notation of, some people call that twiddles, or tilde, I think is the correct name for it. This character, tilde. So we're going to talk about a general relation, A tilde B. A is equivalent to B, or A is related to B. So, this thing, think of this as an abstraction of, these kind of relationships that we have. Equality, greater than, less than, divides, probably loads more, obviously. So this is just some general relation. Now this relation may enjoy these three properties. Okay? These are important properties that a relation might have. Reflexivity says that every element is related to itself. So for every x, x is tilde x. Symmetry says that every time you have x equivalent to x related to y, you also have y related to x. Okay. Now straight away, you'd see some examples of things that are not symmetric. So the normal strictly greater than or strictly less than, these are not symmetric relations. They're not reflexive either. No number is strictly less than itself. Yeah? And if one number is strictly greater than y, then it's not true that y is strictly greater than x. So it can never be symmetric, these relations. Of course, equality is reflexive. Equality is symmetric as well. If x is equal to y, it has to be the case that y is equal to x. So symmetric relations are one where the order doesn't matter. If x is related to y, then y is related to x. Transitivity is where the relation travels through intermediates. What do we mean by that? If it's the case that x is related to y, and it's the case that y is related to z, transitivity is when the y carries the relationship through from x to z. So if this implies that x is tilde z, this is transitive behavior. Whenever you have a property, a relationship here, which is transmitted by intermediates. So y is the intermediate between x and z, the intermediary. If this is always okay, if you have this and you have this, if that implies you have this, and if that works for all elements, for every x, y, and z in the set, then we call the relationship transitive. It has this property. Okay. And these are taken as being nice properties. Equality has them. The relationship of equality acts in all these ways. So because of that, if any relation acts like this, we call it an equivalence relation. It has a lot of the properties, or a lot of the features of equality. And one important property it has is that if you've ever got an equivalence relation, it produces a partition on the set. Okay? So these three properties are what you need to guarantee that when you collect everything that's equivalent to one another in one set, collect everything that's equivalent to other elements in another set, these sets you produce, so-called equivalence classes. This is the class of everything that's equivalent to everything else within this class, and so on. And when you have an equivalence relation, the equivalence classes partition the whole set. We produce this subsystem of subsets that cover the whole set and which have no intersections. So they're disjoint. So equivalence relations are important for that reason. Okay? They split up your large set into a system of subsets, okay, in that nice way. So this is not a partition. A partition is not, say, this kind of thing, which has like these intersections. It'd be fine if these were separate regions. Yeah, a small region between these two regions. But if as I'm kind of implying here that this region is in this subset and it's also in that subset, that's not a partition. Okay? In partitions, the subsets have to be disjoint. So the obvious thing here then is to say that our new relation, the one we've introduced, it is an equivalence relation. It does have these properties of reflexivity, symmetry, and transitivity, which are these nice properties, which mean that any congruence relation modulo any modulus, here I've depicted the one for 6, the equivalence classes, or they're called congruence classes in the case of the congruence relation, they partition the set of integers into this system of subsets. Now, you've got the whole proof of it there, that congruence is an equivalence relation. It's all on this page. Just 3 little paragraphs for reflexivity, symmetry, and transitivity. So what we're doing here in this proof of theorem 4.2 is proving each of these properties for the case of congruence. So proving that it's reflexive, proving that it's symmetric, proving that it's transitive. Now, what are the tools we use for this? Well, you see, the congruence relation was defined in terms of divisibility. Okay, so it's properties of divisibility that we're using to prove theorem 4.2. Okay, because congruence is really just a certain type of divisibility. So the properties that congruence is going to have are going to come from the properties we've already developed for divisibility. So first we're going to prove reflexivity. So we're talking about congruence modulo n. So n is the modulus. So is it the case that every integer a is congruent to itself? Well, yeah, because we remember that n divides 0. Everything divides 0. So in particular, n will divide the difference a minus a. But if n divides a minus a, that's the definition of a being congruent to a. So that fact that n divides 0, you can restate that as n divides a minus a for any a. And that means any a is congruent to itself. So that means that the relation is reflexive. It reflects back to the individual. Then we prove it's symmetric. So we assume that a is congruent to b. Then our goal is to prove that b is congruent to a. If we can do that for every a and b, then it's symmetric. Symmetry, the relationship goes both ways, if it's there at all. So if a is congruent to b, by the definition on the whiteboard, that means n divides the difference a minus b. But again, by basic property of divisibility, this would have been about, I think, multiplying the number on the right by any other number. So here we're going to multiply it by minus 1. If n divides a minus b, it's also the case that n divides minus a minus b. You just stick a minus 1 in front of the constant quotient that you have. So that means that n divides b minus a, and if n divides b minus a, that's the definition of b being congruent to a. So now we know that order isn't important here. If the relationship goes one way, it also goes the other way. If it doesn't go one way, it does not go the other way either. Okay? So it's symmetric. And then the last part is transitivity. Transitivity is often the hardest one to prove, one that takes the most work. And that's, yeah, you can see that, that's 3 full lines here as opposed to 2 lines and a bit. So how do you prove transitivity? Well, you give yourself the two conditions. So you have an A congruent to B and a B congruent to C. And then your goal is to prove that the congruence kind of travels through B from A onto C. So we want to prove this statement then at the end, that A is congruent to C. But we prove it by going via the equivalent divisibility statement. So these two assumptions, that A is congruent to B and B is congruent to C, this means n divides the difference A minus B, and it also divides the difference B minus C. And then, again, theorem 2.1, part 3, this linear combinations result. Here we've got n dividing these two numbers, A minus B and B minus C. So we can certainly say that n divides the sum of them. With the sum of those two numbers, you see the b's cancel out, and we're just left with A minus C. So if n divides A minus B and B minus C, by a property of divisibility, we then know that n divides the difference A minus C. And if n divides A minus C, it means A is congruent to C. Yeah. So that's good. Now we've proved that congruence is an equivalence relation. So we know we'll always get a partition of the integers. It's nice splitting of the whole integers up into these congruence classes. And there's going to be a finite number of them, because for any modulus, the congruence classes are labeled by the remainders that you get when you divide by n. So you're going to have a finite number of congruence classes that partition the whole of the integers. Okay, any questions about that? Okay, so we're going to go on and investigate these things, and the next few chapters look on the Euler-Toshin function, which is strongly related to these modular arithmetic systems. We're also going to look at how polynomials behave on these congruences, on these congruence classes. But for now, let's have a look at exercises 4.1. Yeah, we'll start to do some paperwork here. Actually, these exercises 4.1, this is a staged set of exercises leading up to this final result. So we should look at the final result first. What we'd like to prove and establish is that if you've got any polynomial f with integer coefficients, if f is a polynomial, it's just all in integers, so the coefficients of the polynomial are integers, then it's always going to be the case that if you evaluate the polynomial at A, and if you evaluate it at A prime, now A and A prime are introduced at the top. A is congruent to A prime, modulo n. So if you've got two numbers that are congruent to one another, meaning m divides their difference, or equivalently, when you divide them by n, they both leave the same remainder. A is congruent to A. The final result is going to be that when you evaluate the polynomial at A and A prime, okay, you're going to get different numbers. You're going to get different integers, okay, because A is a different integer to A prime. So these values are probably going to be different, but they'll be congruent. Okay, so evaluating at a polynomial preserves the congruence. If A is congruent to A prime to begin with, the values f of A and f of A prime are also congruent. Okay? So that's nice. That shows that these polynomials behave nicely on congruence classes. If you think about your partition of the integers into congruence classes modulo m, if you take any two numbers in here and evaluate the polynomial f, well, you'll probably hop to another congruence class. Probably. Maybe you'll stay within this congruence class, but in general, you'd hop to another congruence class. But whatever congruence class A goes to, A prime is going to go to the same one. So maybe they're going to pop up here, f of A and f of A prime. Okay? But they never separate. If they're together to begin with in the same congruence class, they're going to remain in the same congruence class when you evaluate the polynomial. Okay? So that says that these polynomials fit well or act nice with this relationship of congruence. So let's see. I think we'll start to do this, and we can look at some more of it in the tutorials next week. Yeah, so let's look at a plus b. Yeah, so we've got two pairs. We've got a pair a and a prime, and we've got a pair b and b prime. So in all these, we're assuming that these pairs are congruent to one another. So a is congruent to a prime, b is congruent to b prime. And we want to prove these properties here. Okay, you've all got this in your notes, so maybe I should get this on the camera. Maybe. Since I'm wearing my suit now. Very nice. Okay. So, number one, a plus b is congruent to a prime plus b prime. How are we going to prove that? So we want a plus b. So if we add the integers a and b, well, if you add the integers a prime and b prime, you're certainly going to get a different integer, probably, because a and a prime could be different, b and b prime could be different. So when you add them, oh, this is a bit weird, isn't it? Not a blank shot. Yes, these are probably going to be different integers either side, but they're certainly going to be the same, modulo n. They'll be in the same congruence class. Okay. So how do we prove this? Okay, I won't look at my solutions. Well, you see, this is what we want. So I want to show that a plus b is congruent to a prime plus b prime. How could I show that? The only way I'm going to show that is if I show that it satisfies the definition. So if a plus b minus a prime plus b prime, that's divisible by n. Okay? So yeah, congruence is defined in terms of divisibility. So we should prove things about it via divisibility. Okay? So from the assumptions up here at the very top of the board, from the assumptions we get that n divides the difference a minus a prime, and n divides the difference b minus b prime. Okay. Yeah. Well, you see, if n divides these two things, then it's going to divide their sum. Aren't they? Isn't it? This was basic property of divisibility. If n divides two objects, it'll also divide any integer linear combination of the two objects, of the two numbers. So here we're simply taking the simple linear combination of just adding them together. And then it's just rearranging that statement there, which gives me this one, isn't it? To bring the a and b together. Okay, so this algebraically, this integer here rearranges to this. Okay. So that gives me that addition works. This shows, you should think about this as saying that addition fits well with the congruence classes. I'll take a little different picture over here. If I want to add an a and a b, so a is going to be somewhere here, b is going to be somewhere here. When you add a and b, you go somewhere else, probably. I mean, you could stay within one of these maybe, but in general, you'll go somewhere else. If you take any two integers, you add them, you'll turn up in one of the congruence classes. What this result is telling us is that addition, this operation of addition, is actually, you can define addition on the congruence classes. So if I take another thing, a prime from this thing, and another integer b prime from that, where is a prime plus b prime going to end up? Going to end up in the same place as this, because we've just proved that a prime plus b prime is congruent to a plus b modulo n. So although these are different numbers, their sum a prime plus b prime ends up in the same place. Okay? So if you add anything from here, from this congruence class to anything from this one, you're always going to end up in this one. So the sum of these congruence classes is well defined. I can add this congruence class to this congruence class, and it produces this congruence. So the fact that addition behaves like this allows me to define an addition of congruence classes. If I want to add these two congruence classes, add these two sets, I have this new operation on the sets. Well, to work it out, to evaluate it, I'll just say take anything from here, add them as integers, and find out which congruence class they go. And it doesn't matter which ones you choose. Because we just proved here that no matter what choices of A and B you make from these two congruence classes, you're always going to find that the sum ends up there. Okay. So that result says that addition fits well with the congruence classes. Now, if addition fits well, a natural question to ask about multiplication. Does multiplication fit well with the congruence classes? So that picture is, if you have integers A and B, they're going to end up, when you multiply them, the product is going to end up in a certain congruence class. What we want to prove here is that with a different choice of representatives, A prime and B prime, we want to prove now that the product A prime times B prime must also end up in the same congruence class. And in a similar way, this will say that multiplication fits well with the congruence relation. Okay. So this is the way to think about these things. We want to prove that AB is congruent to A prime, B prime, modulo M. We know where we're starting from. We're starting from these assumptions. So we know that n divides the difference A minus A prime, and n divides the difference B minus B prime. Here's where I want to end up. How could you ever end up here? The only way you can end up there is if you show that n divides the difference AB minus A prime B prime. Okay, because that's the definition of this congruence symbol. So how do we get from there to there? Well, a little bit tricky. I mean, we can try some things. Multiplication is often harder than addition, of course. I mean, one natural thing to do would be to multiply them together. And when you multiply them together, you do get A times B. You get plus A prime B prime. Now I want minus A prime B prime. And you also get these other cross multiple terms, minus A B prime minus A prime B. Now, if I know that n divides these two, I also know that n divides the product. So I know that n divides this. This is kind of nearly looking like what I want down here, but not quite. So you can do a kind of little trick. You can say, well, what I really want to have is AB minus A prime B prime. So I know n divides all this. So I know n divides all this. I want to say that n divides all this. Now, if I'm moving from here, you see I've subtracted A prime B prime, but what I want is plus A prime B prime. So I have to add on 2 times A prime B prime. And then I've still got these two terms, minus A B prime, minus A prime B. But then I can repackage that. This is what I want, AB minus A prime B prime. And I can write this as minus A into no, it's minus A prime into B minus B prime, and then it's minus B prime into A minus A prime. from the assumptions, I get this. N divides this big long sum. But you see, I already know that n divides this part in this red box and this part in this red box. Okay? Because these are multiples of b minus b prime and a minus a prime. Well, I know n divides those. Okay? So if n divides the whole thing, and it divides this part already, and it already divides this part, n must divide this part here. So from the above lines, I know that n divides this ab minus a prime b prime minus a prime into b minus b prime minus b prime into a minus a prime, which implies that, now I come down to here, this implies that n divides this part at the front, since n divides a minus a prime and n divides b minus b. Okay? It divides these terms in the sum, so therefore it must divide the difference, because we know it divides the whole thing. Okay? So multiplication is often a little bit trickier to handle than addition. That mightn't be the best, most elegant way to prove it. I probably could make it a bit, shrink it down a little bit. So we know n divides this whole sum from the assumptions. We already know n divides these two parts separately from the assumptions. So therefore n must divide the difference. So that shows that multiplication fits well with these congruence classes. I can define in a well-defined way what this congruence class multiplied by this one is. I evaluate it by choosing representatives, and it doesn't matter which representatives I choose. I always land in the same congruence class here. So I can say that this congruence class is the product of these two. Okay, so we'll pick this up at the tutorials next week.